Geihs. I'm from Web3 Auth. We do distributed key management, and this is joint work with Hart Montgomery from the Hyperledger Foundation. And it's about a distributed PRF protocol and how it applies to scaling distributed key management. And the preprint is available at ePrint. You can find it if you search the title. So I guess. So that is kind of a rough overview of the core contributions. So we were looking at the lattice-based PRF, which was proposed in 2013 by Bonnet, Levy, Montgomery, and Rakutanathan. And we show how to turn this single-party standard PRF into a distributed PRF protocol, which runs in 8 online rounds. It is robust to, so it is thresholdized, so it's robust to server failures, and it is composable with other threshold signing protocols, which is important for our application. So what is the general motivation behind this? Yeah, we are doing distributed key management, and we have to manage a lot of keys. So when we have a new user registers with our system, then we run a DKG protocol usually, and we generate some key shares for the user. Then we have to store all the user keys. In our case, this is actually millions of key shares currently, so each server stores a share of each key. And sometimes we also have to do some maintenance work in order to refresh the shares, or maybe we have to migrate shared databases if we want to transition, like kind of upgrade the system. That can also happen. So all of that now actually requires an amount of work and storage, which is linear in the number of users. And the question is, can we do better? Like, can we make the storage and workload independent of the number of users in the system? And the answer is yes, we can if we have something like a distributed PRF that works for our application. So think of it as a PRF function where the input key, the master key, is secret shared. It gets a public user identifier, so the user identifies with the servers. He gets maybe a Google Auth token or something like that, which is his user ID. This is public information, and then we derive the user key shares from the master key and the public identifier of the users. If we have something like this, then we can just derive user key shares on the fly. We only need to store the master key, and we can derive user key shares on the fly. We don't have to store, as I said, the master key. We only have to store the master key. We don't have to store the user key shares. And the maintenance now also becomes a constant, basically. So if we want to migrate the shared databases, we just have to migrate the master key. Or if we want to refresh the key shares, we just have to refresh the master key shares. So basically, all of our work is now constant in the number of users, which can be really nice. Like we got rid of a lot of complexity. And the question, of course, is how do we realize a PRF, a distributed PRF protocol that is useful and works for our application? So what are the properties that we are aiming for? So we have public inputs, as I said. Basically, the input space should include all of our user identifiers. Then our outputs should be secret shared outputs and should be distributed according to the key generation algorithm of the scheme that we target. So think of ECDSA secret keys. So our output should be secret shares values of ECDSA secret keys, for example. Next, we want some robustness in our system. So if some of the servers are not active or even malicious, we still want the system to be functioning correctly. We ideally want to rely only on standard assumptions so we can actually use this in production without too much risk. We need typically a low round complexity because we don't want to wait have our users waiting for, let's say, 10 or 30 seconds until they can log in and use their keys. And last but not least, it should be composable with other protocols. So we want to run a threshold signing protocol in particular afterwards. Yeah, so next I will tell you basically how we came up with a protocol that works for that scenario. So we started from looking at this PRF from 2013, and it is a lattice-based construction. Basically, yeah, the secret key is a vector over set Q. The input in the standard construction is a bit string of length L. We have two matrices which are public, which are kind of used to map the public input or the input of this PRF onto a random, like randomize the input in some way. Then there's a multiplication by the secret key vector, and in the end we compute all of this modulo Q, and kind of what introduces the hardness is the rounding. This is a special mod P rounding, which is basically, do I have a pointer here? So this is basically scaling down the result of this inner computation by a factor P over Q, and then throwing away the lower order bits. You can think of roughly like this. Like we scale the result, and due to that, by rounding and throwing away some bits, we introduce some randomness, which is unpredictable, and this PRF is actually shown to be as hard as the learning with errors problem. So learning with rounding is the immediate problem that this describes, and it can be reduced to the learning with errors problem. So this is actually yeah, thought to be post-quantum secure as well. Okay, so this is like the single party PRF that we work with, or that we have been starting with. How do we turn this into a distributed PRF protocol? So basically, I'm going through now three optimization steps that make this more practical and will lead to something that can be evaluated efficiently in MPC. So the first observation is we can actually reduce or replace this matrix product that depends on the input X by, if we just assume the random oracle model and have a hash function that maps input bit strings to a random matrix of size L times M, then we can just replace this product, which is just a public product, but it's some work to compute this, and we show that we can basically replace it by a hash function call, and that's already much more efficient and saves some computation. Sorry? 5 minutes, okay. I'll try to speed up a bit. So the next observation is, okay, we're actually quite free how to choose the parameters Q and P. So if we choose them as powers of 2, then these modulo Q and the rounding operation become basically bit truncation operations. So modulo Q is just throwing away the higher order bits upwards from the log2 Q bits, and the round P operation is just throwing away the lower order bits. And now we have something that is quite is a nice representation of the same function as here, but we will see this is much easier to think of in MPC because these bit operations we can do efficiently in MPC. And okay, the counting is wrong, but anyways, the last thing we need is we have an output vector of our PRF, but we actually need something. We just need a single element over a prime modulo over a field, over a prime field, basically. So we have an output vector modulo P, where P is a power of 2, but we need something that is a single element, or at least we need something that is a random element in a prime field, and there's this known conversion to basically basically accumulate these elements so that we get something random in the prime field. So that's basically it. So then the last observation is there are already results for how to compute these functions in MPC. So the truncation of the higher order bits can be done in 1 plus log q rounds. The truncation of the lower order bits can be done in 1 plus log q over p rounds. And this is just a local operation, and this is also just a local operation. So for concrete values, we did an implementation as well. You can look it up. You will find it via the paper. So assume we have a base field modulo as 256-bit prime. We have some different values which either optimize a bit for the round efficiency or the data communication efficiency. So we have 2 parameter sets which aim roughly both for 128-bit of security. Lattice dimension is fixed to 512, and the vector size is basically like how large the vector is and how many output elements you get before this reduction step in the end. Yes, and we kind of measured our implementation, which is done in the MP-SPICE framework using maliciously secure SHA-ME secret sharing as the base protocol. And we can see that basically the previous works that were looking at distributed PRF protocol are more optimized towards communication complexity, and we outperform then in terms of round complexity by an order of magnitude. So if you need something that runs like a PRF, a distributed PRF, which runs in a small number of rounds, then I think looking at lattice-based constructions, or in particular this protocol, is quite nice. And I should note that this is all without any network latency, so this is local communication. There is some pre-processing cost to all of this. I think it's 2 rounds and a bunch of communication, and our protocol kind of trades off communication for round complexity. So we need more communication than the other protocols, especially also in the pre-processing phase. And one interesting question is like how we do these bit shifting operations internally uses a lot of secret shared random bits, and that's kind of the communication bottleneck that we have. It's still okay, I think it's still practical, but it would be very interesting to know if we can, or how we can generate a lot of secret shared random bits more efficiently. That would drastically improve the communication even more. Yeah, that's it. Thanks.
Does anybody have questions? That was a very technical talk. I see one hand up there. Super.
So, hello. Yeah. So you mentioned that some connection with DKG in the beginning, right? So you were saying like you can construct a DKG from a distributed PRF sort of generically, or how do you get the public key structure?
I mean, we don't construct the DKG. We basically, then it's a distributed key derivation instead of a distributed key generation. Yeah.
Right. So, okay. So it's a key derivation. Okay, that makes
exactly.
sense.
Yeah. So you have a secret shared master key, a public user identifier that you get from authenticating the user, and then you get some user secret key shares.
Okay, that's fine. Thanks. Yeah.
I see one hand by Luis here, Pascal, and one more on top.
Thank you. When you say number of rounds, do you mean like is that the multiplicative complexity of the operation?
I mean the number of rounds the protocol needs, like the number of interactions between the parties, basically. So,
but that's because of the choice of the MPC protocol you're choosing, right?
Exactly. It correlates with the protocol and the parameters that we choose. So it depends a bit what P and Q is, but that's roughly what you get. Yeah.
Okay, so it doesn't have to do with the number of parties?
No, it's independent of the number of parties and roughly also independent. It's independent of the lattice dimension, which determines kind of the security of the lattice assumption by a large part. So,
but in theory, could you, let's say, do a constant round protocol if you were to use different tools like garbled circuits and stuff like that, even if it were to be more expensive?
Maybe. I'm not sure. Maybe with different techniques, but yeah. 8 rounds is for our application already quite good. Much better than 100 rounds. So yeah.
Thank you.
I think there's one more question up there. Yeah.
I think it's a similar question, is that because you can see here is that if you have about 200 or several hundred rounds, and if the user and the machine have a long latency, then it will actually be pretty bad. And like 8 and 10 is actually very impressive number, very, very impressive. I would only have one question, is that like how do you compare with like using like constant round garbled circuit based protocol, and you don't use those like expensive hash function, like you just use AES. How do you compare this construction with that? Because that one would have the constant round, and like for AES, like I don't know, I have the feeling that the data communication might be actually higher. The time is a little bit uncertain, but it might also be quite competitive. What do you think?
Yeah, it's a good question. We haven't looked at any garbled circuit construction. I have looked at AES evaluations, like compiling them to Shami-based protocol, and that took like, I think, 50 to 60 rounds or something like that. So the other thing that we really need is robustness. So we want to have some threshold properties. I don't know if you could do that with Yao's approach.
Usually not.
Yeah,
right.
So definitely worth looking more into other protocols as well, but like this was a good candidate for us, and yeah. I think the first one to explore these kind of lattice constructions in this setting. Yeah.
Yash also has a question.
So if I understand correctly, the setting is like 3 parties, 1 corruption.
This is the evaluation that we have, but you could also compile this to a dishonest majority protocol as well. I don't know if that would affect the round count, to be honest, but like the evaluation that we did is for 3 parties with a threshold of 2, but you could compile it to different settings as well.
I mean, okay, but I guess I'm wondering, for instance, why something using like replicated secret sharing wouldn't work.
I saw that you're using something like this in the paper. I only saw it basically after we. I think it would be interesting to talk about this. I wonder if it could achieve all the same properties that we are trying to have, but yeah, maybe we can talk briefly about it offline, like what it can do and what it maybe can't do if you do replicated. I think it would need some more communication, or.
I mean, no, it's non-interactive, no communication.
Okay. Because you don't have to go through the PRF computation at all, I guess.
Yeah, it's black box in the PRF, so you can like get shares of. Yeah.
Basically, I wasn't aware of this replicated secret sharing approach, to be honest. And I think this contribution for sure is like exploring how can you. Maybe it also has implications for CK if you want to have a PRF evaluation as a CK circuit. Yeah, this is, I guess, the core work here. I'm definitely interested to hear about the other approach a bit more detailed. Yeah.
Thanks.
Any more questions? I don't see any hands. I have one. Perpetually, when you work at Web3 Auth, you all have been leaders in that space. What would you say is the most requested algorithm from clients? Is this the one? Is this it?
This is, I think, an internal effort that we just want to look into, like how can we reduce the effort, because this is actually something that is a small pain, like really there's a lot of keys and some users are not active anymore, but you can't throw away their keys, right? So reducing this this effort is relevant to us, but in terms of like actual production system, that this is not something we're using yet. We are using DKLS for threshold signing, and yeah, a typical key generation protocol, distributed key generation protocol. So
was this an area of research or interest that was generated from client requests? Just trying to understand where.
Not sure. I have to ask our CTO for that.
Okay.
He gave me that research topic, so
Makes
I
sense.
don't know
Okay.
where it came from, to be honest.
Great.
But yeah, maybe.
Thank you so much for your time, Matthias. Everyone
Thank you.
give a round of applause for Matthias.